Welcome to Unwired Learning. In this video, we're going to talk about advanced nodal and mesh analysis. And what do I mean by advanced? Well, in particular, we want to be able to solve for voltages and currents in a circuit. But by advanced, we mean that we might have dependent sources in that circuit, or we might have something that we call a supernode, or we might have something that we call a supermesh in that. Over here is an example of a circuit that contains a dependent source, and that dependent source also happens to be between a couple of meshes, and so this kind of circuit would fall under the category of advanced analysis. Let's take a quick look at an example where we do node voltage with a dependent source. As you can see in this particular circuit, we have a dependent source over here on the right for I phi, where I phi is the current across this 4 ohm resistor. In doing this, we need to look at our different nodes in this case. And again, we're looking at what we call extraordinary nodes, nodes that connect more than 2 different elements. So in this case, we have a node right here, we'll call that node 1, and we have a node right here, we'll call that node 2. And so at node 1, we can write the equation. And again, what we're looking for here in nodal analysis is that all the currents that are leaving the resistors must equal 0. So our first equation is V1 minus 10 volts divided by 3, and our next part is plus V1 minus V2 divided by 4 plus V1 divided by 10, and that must equal 0. In this case, let's go ahead and rearrange and then simplify. So for all the V1s, we have a 1 over 3, a 1 over 4, and a 1 over 10. And then we have a 1 over 4 minus for V2. And then we have a minus 10 over 3, but we'll move it to the right. Looking at this, we can see that our least common denominator is 60. So we're going to multiply both sides by 60, and we'll simplify the equation from there. In this case, we find that we get 41 V1 minus 15 V2 equals 200. Now for node 2, we have the equation of V2 minus V1 divided by 4 plus V2 minus 4I phi divided by 5 plus V2 divided by 20 equals 0. And now let's go ahead and simplify that circuit, and we get that equation, and we get minus 1 over 4 V1 plus a combination of 1 over 4 plus 1 over 5 plus 1 over 20 times V2, and that is going to be minus 4 over 5I phi equals 0. And then if we look at this, we can find that our least common denominator is 20. So we'll multiply both sides by 20, and in simplifying that, we get minus 5V1 plus 10V2 minus 16 I phi equals 0. Now, in this case, with the dependent source, we end up with this extra variable I phi. However, what we can find is that we can write this variable I phi as an equation of V1 and V2. So what is that equation? Well, look here. We can see that I phi goes through this 4 ohm resistor, and it goes from the direction of node 1 to node 2. So we can say that V1 minus V2 divided by 4 ohms is equal to I phi. And now we can substitute that into our last equation that we just wrote for node 2, and we can simplify that equation down. In doing so, we get minus 5V1 plus 10V2 minus 16 times V1 minus V2 over 4 equals 0. And then multiplying 16 divided by 4, which gives us 4, and then moving the V1s and V2s around respectively, we get minus 9V1 plus 6V2 equals 0. And now we have our two equations. This one over here on the right, on the left, 41V1 minus 15V2 equals 200. And this one over here on the right, minus 9V1 plus 6V2 equals 0. And that is our system of equations. And we can put those into a matrix operation and use something like MATLAB to solve for the values of V1 and V2. Doing the matrix, we get 41 minus 15 and minus 9 and 6 times V1, V2 is equal to our values of 200 and 0. And then solving that, we get V1 equals 10.81 volts and V2 equals 16.22 volts. And those are our final answers for this particular problem. Now let's go ahead and look at a problem where we have a supernode. In this case, it may be obvious, but our supernode is a result of the fact that we have a voltage source here between a couple of nodes. So if we're looking here and we look carefully, we should see that we have an extraordinary node over here on the left. We'll call that node 1. We have an extraordinary node here in the middle. We'll call that node 2. And we have an extraordinary node here on the right. We'll call that node 3. However, V2 and V3 are not exactly independent because there is a voltage source that exists between node 2 and node 3. Because of this, what we're going to do is essentially combine these two nodes together into what we call a supernode, and we'll write equations for that entire supernode. And the reason that we can do this is because the node 2 and node 3 are not independent. There's a relationship, well, and that relationship is 2Vx, right? The difference between the voltage at 2 and the voltage at 3 is, well, the opposite of that, but the difference between 3 and 2 is 2Vx. So let's go ahead and look here over at node 1. And for node 1, we can actually already write the value of voltage that we would get for that. Because there's a independent voltage source that goes from node 1 down to the reference point ground, then we know the voltage at node 1, and that is 8 volts. So V1 equals 8 volts. And now we'll look at our supernode. For our supernode, we'll start with the side on node 2, but then we'll continue to write the terms of this equation moving over to V3, or node 3. So let's start with the first equation, or the first term for node 2. We'll get V2 minus V1 divided by 12K. And then our second term would be plus V2 divided by 8K. And now we'll move over to our node 3. And we get plus V3 divided by minus V1 divided by 8K for that resistor at the top. And plus V3 divided by 12K for the resistor on the far right. And all of that must equal 0. And it has a constraint, and the constraint is because of the fact that we have the voltage in between nodes 2 and 3. So our constraint is that V3 minus V2 must equal our voltage there, which is 2Vx. And we also might recognize that the value at V2 is Vx. And so we can put these two equations together and we can come up with the fact that V3 must equal 3 times V2. So now let's go ahead and simplify our supernode equation and plug in the value for the voltage at V1 and this newfound constraint that we have, and then we'll be able to solve for the values of V2 and V3 respectively. To simplify this equation, I'm going to multiply both sides by 12K. As you can see, that would be, not 12K, but rather 24K, because that would be our least common denominator in this situation. So when we do that, we'll get that we have the first one, we have 2 V2s, plus we have 3 more V2s, so we have a total of 5 V2s. And let's see, we have a minus 2 V1s, and then again we have another minus 3 V1s, so we have minus 5 V1. And then for our V3s, we have 3 V3s right here and 2 more V3s right there, so we have plus 5 V3. And all of that must equal 0. Plugging in for our value of V1, we can write minus 30 plus 5V2 plus 5V3 equals 0. And then plugging in for our value of V3, which is equal to 3V2, we will get 5V2 plus 5 times 3V2 equals 30. And then that gives us a total of 20 V2s equals 30, and that means our V2 equals 1.5 volts. And now 3 times that is equal to V3, so V3 equals 4.5 volts. And those are our unknown voltages, along with our V1 voltage over here on the left.